So for today, we're going to go over a very popular proof style called proof by contradiction, with a similarly very popular problem that we prove by contradiction, which is to prove that the square root of 2 is irrational. So what is the very first step for proof by contradiction? I call it PBC, proof by contradiction. We start by just assuming the exact opposite of the statement that we're trying to prove, and then eventually get to a point at the end where we see, oh, there's a contradiction, therefore the original statement must have been true. All right, so what would be the opposite of this statement that root 2 is irrational? Simply that to assume square root of 2 is rational. So we know irrational numbers like this one, root 2, or maybe pi and other numbers are simply numbers that cannot be expressed as a ratio. If you try to divide them, the numbers go on forever and ever, these non-whole number values. Whereas rational numbers can be expressed as a ratio or fraction in simplest terms. And so that's what we can get out of this assumption we just made. We're just going to try to work with what we just assumed here. And so from this, we can now safely say that if root 2 is a rational number, that it can be expressed as a ratio in simplest terms. So, right, this is the following conclusion from the first line. Root 2 is two numbers a over b, so a and b are integers. And a over b is in simplest terms. It's been reduced as much as it could possibly be. So that's going to be super important later on, as we just want to work with unsimplified ratio. We're going to work with the ratio form of root 2 in simplest terms, and from there, I want to get rid of that square root. So why don't I just square everything? And so what that looks like when you square the left and the right is you end up with this equation, right? Or equality. Now let's move some things around, like that b squared can move up to the other side if I multiply both sides by b squared. Then I'll end up with 2b squared on the left, a squared on the right. Oh, and this is special. We talked about in our video about direct proof. Check out that video to see that whenever you have a quantity that's a multiple of 2, that means that must be an even number, right? So even numbers are simply multiples of 2. So I want to make a point here that a squared is even, since we got a multiple of 2. And then if you also refer back to that video on direct proof, you'll notice that, I'll put this here, that we proved, make this a note. So we proved that a squared is even only if a is also even. Okay, so for that reason, we get to now say just all this just from root 2 being a rational value, and then working our way down to get an even number, right, from a squared. We also are provided now that a is another even number, so we get to write a itself as a even value or multiple of 2. So k is just any integer that makes a an even value as a result, right? So look at that sequence of conclusions and results we're getting. A is also even, and I'm rewriting it as 2k. And so a squared is, we said 2b squared, right? from before, you'll recall. But also from this definition of a being an even number, we also get that it's 2k squared, which can be rewritten as 4k squared if you expand. And so now I'm simply going to take note of this end product here and the beginning or previous equality we got from a squared and set those two equal to each other and see what happens. 2b squared equals, I promise the contradiction is coming, 4k squared. And then if you reduce that, right, both of them have a value of a factor of 2. You can reduce that down to b squared simply equals 2k squared. And look at that definition of even numbers really shining through in this problem. B squared is also even. And hopefully you remember what we're going to do from there using that note or direct proof we used in another video. Now we can also conclude that B, therefore B, must also be even. It looks like the end of the proof here. Whenever I write therefore, I usually save that for when I'm at the end of the proof, but there's a little bit more left. Really think about this. What have we shown? We have shown A is even. B is also even. And go back way up to the top here when we said root 2 was rational and in simplest terms. Now, do you think it's possible to have a ratio, a fraction, where the top and bottom are both even numbers, numerator and denominator, and still be as simplified as possible? No, that's the contradiction, right? So if we have A and B both even, that means they did have a common factor of 2, and so we've contradicted our original assumption, which we'll write down fully here. Contradiction. Nice and big letters. If A and B are both even, then that original root 2, which was the ratio A over B, is no longer in simplest terms. Whoops. That's okay. We wanted that contradiction because now we can safely conclude root 2 was never rational to begin with. Or as the original statement wanted had it written, it's irrational. So there you go. Finished that proof by contradiction that root 2 is an irrational number.